Hello YouTube, iFixItAll here, Team iFixItAll. I generally can't stand it when I have not exhausted all resources before I give up on something, and I'm happy to report I'm making some progress. But first let's talk about that heating element and the way it's made. The copper tubing around the heating element. You'll have to back up a few videos, people, if you're just now stumbling across this. So like November 18th, 2025, but this is a STIEBLE ELTRON Tempra24 hot water tank that I've extracted out. It's an older one. I've been exploring how to repair it. Sorry for so many parts, but I just like documenting this stuff. So the heating element has a corkscrew type heating element wire inside the copper tubing, but it is encapsulated with porcelain or some other non-conductive material, and electricity travels through, heats the porcelain, heats the copper, water passes by the elements and comes from your source, parallels into each tank, comes out and goes to your spigots. And my problem on previous videos was I did have resistance from these terminals to chassis. And I was able to isolate that this is element number 1, because you got to look at your bottom for the minus sign. You'll see a minus sign and see how it points to my hour on TV. It points to our 8 o'clock and our 2 o'clock. That diagonal thing, that's element number 1. So you read from here to here, and that's an element. And then from here to here is another element. And then from here to here is the third. And we've got this all woven in. The outer 3 turns is element number 1. You can see how I'm talking about outer 3 turns, because it looks like there's a significant difference between the element number 1 and then the inner is element 2, which is 2 turns, and element 3, which is only 2 turns. We won't go over the arrangement, but I'll show you what my progress is. In previous videos, I was having resistance readings from everybody to chassis. So let's see where we are now and how I got there. Okay, so hopefully you can see this. Where's my little scratch mark? I've been referencing the same reference ground for a while. Okay, so element 1 goes from this stud to this stud. Element 2 is from here to here. Element 3 is from here to here. So you want to have no reading on your meter from any lug to the case. Alright, so I'm going to go to element number 2. Watch this. From element 2 to the case, now I've got nothing. That's both sides of element 2. I'll go to element 3. Nothing. Okay? Now we're going to go to element 1. I don't know if you can see it or not, but that's reading 20 meg. There's a little lowercase m. I'm going to zoom in on the meter a little better for you. Move this in frame a little better. $20 meg. $21 meg. Now, what I think is going on here is inside the tubing, there's been trauma on element number 1, because of course there's trauma. We had a blowout. Okay, you can see the little squirrely, corkscrewy winding in there. The metal winding. And the white porcelain that encapsulates it. That winding is not allowed. It's forbidden from touching the copper tubing, because that winding is taking the 120 volt or 240 volt AC and generating heat. That material in there, that winding, is not made of copper. It's made of various metals that have a resistivity per inch, or so many ohms per foot. And the way they increase the length of that is by running it in spirals. Kind of like that spiral wound notebook is not 2.5 inches long. If you stretch it out, it's going to be probably 20 inches. So you can gain more distance by spiraling it. And you also gain in more resistance. Therefore, you can make some heat, and it transfers to the elements. How did I fix this problem? Well, since I have experienced something called carbon traces in electronics, where something would short out or be a place where current's not allowed to be going, it will bleed off of a leg of a component, like a resistor per se. It would bleed off because this has got some corrosion, and it'll bleed off to ground, or in this case, the case of the hot water tank. Arrgh. Hang on. Hello. Goodbye. I think I have a carbon trace inside this element somewhere. The element number 1 is this outer band, these 3 turns here. That somewhere from the element wire on the interior, there is a path for current to leak out and touch this copper tubing. So I tried one of the old tricks of breaking loose a bad corroded connection that's kind of trapped, if you're able to, is to add heat. If you look at the discoloration of all this tubing, I have been laying down some serious heat on this thing, and I've been using my torch, just a basic propane shop torch, not one of those hotter ones that has a trigger, but one of these kind. It's just the old-fashioned kind. And you heat the copper tubing up, and it'll swell and pull itself away from the porcelain interior. It'll kind of stretch the metal, and then when it cools, it retracts, basically shearing off that connection, that carbon trace, like there might have been some arcing inside these elements. So that's how I've got myself in a situation where now I've got 20 meg on here. Now I would probably put this back in the hot water tank as it is, because 20 meg is really not a big deal, but I'm trying to get it to be open circuit. So I'll show you how I did that. And number 2, pointing back to an older video, I remember being troubled on how am I going to get this element out if I want to do a repair. And my logic was, let me just cut it off. Got my point with. Let me just come up about a 1/4 inch and then cut. Oh my God! Hang on. You know, if you're a telemarketer, your objective is working because it's funded by China, I'm sure. The more often you can prank or scam call someone, the more time you take away from that American's task they were involved in, where they have to come back and regroup, and receiving one of those calls and then reintegrating back to what you were doing more than 70% of the time costs you about 2.5 to 4 minutes. That call may have been the thing that triggered you to say, screw it, I'm going to go refill my coffee, or screw it, I'm going to go take a break for a second. They're trying to take your time and cause inefficiencies. The elements here, I suspected there might have been a carbon trace somewhere in here. So let's go heat this up, and let's try to get this 20 meg reading on element 1 to no continuity at all. Hang tight. Carbon traces are somewhat common in vacuum tube radios, and they're also fairly common in a lot of high density, high compact electronic circuits where connection points are real close to each other and so on and so forth. But let's get some fire. Now I'm just going to heat up element number 1. And I'll get this to a point where this copper starts changing color, and you can actually see it wave in different colors. Again, the heat is to expand the copper off the porcelain, to crack any corrosion. And if you're really having a hard time understanding it, just think about getting a nut loose off of something that's real rusty. But if you just heat the nut up and try to avoid putting any fire on the physical bolts where the threads are, that nut will expand and crack that corrosion connection loose, that rust connection loose, and give you the ability to remove that nut off of that threaded round stock easier. I'm going to try to really lay the heat to this thing. I'll pause you all for a little bit. Okay, watch the top arches right up there. Watch them change colors. That's not light reflecting. It's actually the heat swelling that copper up. Now, since and again, sorry guys, but previous videos, you gotta watch them. Each one of these connections down at the base right here are cracked. I have a theory, I'll get to that in a minute. I'll probably get to it now. I'm making sure I heat this. I believe that where those porcelain insulators are, down along the bottom, that high temperature epoxy they used becomes conductive over time. Because I noticed I was able to get rid of my resistance readings on my element number 2 and 3, which is the smaller interior portion right over here. These 3 loops is element number 1. I was able to get rid of the heat, the resistance readings, by heating up the terminals at the bottom. If I heated up the terminals at the bottom down here, just doing this, heating down there, I was really surprised about that because I was actually doing something different while I was heating to try to break any carbon traces loose. And I discovered that that epoxy started bubbling and running out. And then as a result, when this whole unit cooled off, I don't have any resistance anymore from element number 2 and 3. But element number 1 is trying to hold on to about 20-some meg. Now with cracks being present down on the bottom of each one of these connection points, that means water can get inside And if water can get inside, then that's going to tap water. If it gets inside, that's going to allow electricity to conduct from your source power directly to the heating element and short it out on the interior of that copper. This is supposed to be a watertight connection. Water never gets inside those tubes. Water flows around those tubes. I like how copper just acts when you're running heat against it. That's so weird. Now this crack down here in the tubing, I've focused heavily on it as well because that was sitting in direct water. Now just so you know, physical water itself is one of the Class A, world-class best insulators there is. Water does not conduct electricity. H2O does not have enough electrons in its valence shell to be conductive. However, tap water consisting of H2O and other elements like your magnesium, everything else, well then that's why tap water conducts. The actual H2O is non-conductive. Just take a look at your periodic table and see how many electrons are available for conduction on hydrogen, and look at how much electrons are available on oxygen. Right now I'm just heating the hell out of this element. This is my first task, is to clear those resistance values. And either I'm dealing with a moisture that's stuck inside the tubes due to the cracks at the bottom, or I'm dealing with a carbon trace, the arcing in its own places. I'll be right back after I get done heating. And I'll let this cool off and we'll see how well we did. See if we improved anything. Alright, so that's got to cool down because it's right now it's a heater. But I'm thinking, we were talking about this lower part here and how these are actually down low. The protrusions, those round stalks sticking out, that's actually the element that just pushes through the cap. And then they dress the ends and I guess they CAD weld on, they attach a element wire. I don't know if that comes in the element itself. I know there's the spiral wound thing, but I don't know if there's a solid core to that as well. But either way, they CAD weld onto the lugs and voila. But this has got to cool down for quite a while. I'm letting it slow cool. I don't want to quick cool it with water because I don't want to encourage any other fractures. Now back when we were talking about how do I remove this whole element assembly, and I left a 1/4 inch of tank down here so that I could maybe flare out my existing tank and slip it in there. Well, the length of the heating element comes all the way to the very end up here. I thought I could flare this lip out a little bit, widen it, and slip it over that 1/4 inch of tubing that I've got on the slip this over my 1/4 inch that I left behind over there after it's tinned and all that with plumber's solder, and then flare this out a little bit, slam it on, because there's obviously going to be a little bit of headroom in here. That's not the case at all. There's zero. I mean, if I have any clearance at all, one particular element is literally like a 1/4 inch. One turn of element 1 is like at least a 1/4 inch taller than everybody else. Those 3 turns right there that you're looking at is element 1. And then element 2 is only 2 turns, and element 3 is only 2 turns. Putting this thing up in the container over there, I don't have that much headroom there. I was wanting to leave like a 1/4 inch, but I left like maybe 3/16, but that's all handwork by hacksaw. That little shoulder right there is supposed to be inserted up into this. But I just don't think I have the room for it. There's no clearance. I mean, I literally think that one tall turn on element 1 is like all the way up in here. So we'll see. Let that thing cool down. Let's check our resistance. Alrighty, let's see what we got after it cooled down. We're checking resistance now. So I've got my diagonal hash mark there. It points to here, so that's element number 1, which is the 3 turns. That's what we're focused on. We're seeing what each terminal to chassis reads as far as resistance. Alright. Ruh-roh. Looks like I made things worse. 4.9 meg, 5 meg, and it's creeping up and up and up. Let's go to the other terminal. It's creeping up. I wonder if it has something to do with it cooling down, because right now it's room temperature. I mean, I should be able to grade it right now, 5 meg. I wonder, let me set up something here. Let's put a voltage on this and see. I'm going to bring power into terminal one side of element 1. Let me work this backwards. I'm going to bring 120 volt neutral to the chassis, and then through a current limiting resistor, bring power into this terminal and see what the voltage drop is across that resistor. I've got it set up right here already. Let me get this situated. Alright, that's what I've been thinking about doing. So I've got a current limiting resistor. There's chassis. Set up chassis. Scrape some of the oxidation off, so I got a good neutral connection. I have a basic extension cord coming in. One leg of the extension cord is right here, this little tiny wire that travels to the green. It's kind of weaved into this jumper. And then I've got a black, that's the hot leg of the 120 volt outlet that goes around and around and around, goes in over here through this current limiting resistor, and I'll hook that up to one side of element 1. Dang it. There's one side of element 1 hooked up. So I've got chassis in the game. Power comes in, goes to the black, through the resistor, through the red, to this one side of element 1. And if it's bleeding through, it'll go through this return here. I'll plug my cord in. Sounds sketchy, but I'm just trying to see what the actual voltage drop, the voltage is. How much load is actually going through from the element to ground. How much is what's the value of the ground fault? Needles cracked. Needles, knees cracked. Alright. Let's plug in. Let's see if our resistor gets hot. It's staying cold as a cucumber because it's energized right now. Power's coming in here, and if there is a short to ground, then it's going to be catching ground anywhere on that element. Shut up. Let's go to AC volts. Let's see what our voltage drop is. Notating what our voltage is on our meter with no leads hooked up. You're gonna, when you go to AC volts, you could have some driftiness going on. So what do we got across the resistor? A half a volt, 0.5 volts, or 500 millivolt. So if we have that naturally aspired, and the tech support guy says that when the unit's not running, there is a tiny amount of current and voltage going through the elements. If that's 500 millivolts, which I doubt it would be, but it could be 50 millivolts. It could be 3/4 of 1 volt at 250 millivolt, quarter volt. Because right now I got a half a volt that's faulting to ground. Let's see what we got at terminal 2, or this other end of element 1. Okie dokie. Karaoke. Half a volt again. Resistor's not getting hot. Turn my meter off. Unplug my dangerous little setup here. Check my resistance reading. Ohms. Because we just don't want to believe our meter. Yeah, it's reading 3.5 meg. There's 4.7 mega ohms, or 4.7 million ohms. 4.8 million ohms, 4.9, 5 mega ohm. Well, I made matters worse on that last heat up round, because before we started we had 20 meg. Scotty boy, if it ain't broke, don't fix it. Alright, so I guess where I'll end this video is I'll heat this up 1 or 2 times on my own time. If I get it to a point where I'm ready to reassemble, then there will be a final part on this. But I'm going to have a band to go on here. Here's what I did do, though. I cleared the fault. And I want to point out, again, when I was heating, and this is probably a note to STIEBLE ELTRON, if they watch this video, because I'm sending it to my tech support guy, the link. If he watches it, he does. If he doesn't, he doesn't. But still, I cleared 66% of my faults, which is 2 elements, when I was heating the bottom of this. I was heating the bottom, and I can't recall why I was heating the bottom. Oh, that was because I was trying to burn off some of this corrosion down here. I was prepping because I had put different cleaners in there, and then I was heating. After I got the cleaner out, I started heating up, thinking, well, maybe it's if I can break that solder loose, or I can extract these elements. I was thinking about a few things. Can't quite recall. Let me see. I remember now. I was heating the bottom because I had been suspicious of the idea that when these individual conductors protrude out. Turn the overhead light on. Dang it. These individual conductors poke out, that adhesive that's in there, the sealer, had become compromised and was actually conducting from this tubing to that conductor. And I heated up a whole lot, and I cured element 2 and 3, and I continued forward, heating up everywhere I can, and to include oozing some of that sealer out of here, and also reflowing some of that solder that's down where all these tubes are cracked. And it did kind of reflow, but it went elsewhere, and I need to solder these tubes again. Once I can do that, I can build a copper band around the base of this, around the outside, slide this up in it, and braze it back on. This is a long way around trying to fix something, but I learned a lot. One common denominator is each one of these elements are cracked at the base. And so I'm speculating if we had a power outage sometime, or maybe I'm suspecting that if I had to drain my water for some reason here a while back, that perhaps that small amount of current flow overheated element 1. It doesn't answer as to why element 2 and 3 are cracked. I don't know why they're cracked. I think they're compromised when this part is brazed on, because this literally looks brassy looking. The bottom cap looks like solder. But here, this bottom cap almost looks brassy looking, but it could be solder. That too much heat applied stress cracked these initially. I just don't know and I don't know if they resistance check these at the factory when they fill them up with water. I guess they have a test bench where they test. Right now I'd have to build a band to go on there to affix the tank to this. We're still not fixed, but I did get rid of the resistance by heating. So there you go, guys. Future part whatever coming up.